In this video, we'll talk about surface integrals of functions and vector fields. Let's start with functions. So let's imagine that you have a surface in space given by a vector function of two variables or parameters, u and v. So each component of this vector function depends on u and v. They are functions of u and v. So x, y, and z, they are all functions of u and v, functions of two variables. U and v, these parameters can change over some domain D. So there is a domain over which u and v change. And then we want to talk about the surface integral of a function f of three variables. So this is a function of x, y, and z. We want to talk about its surface integral on this surface, over this surface S. And it will be defined as the double integral over the domain D of f as it takes its values on the surface multiplied by the length of the cross product of r sub u and r sub v, so the partial derivatives of our vector function. So we take this vector function, differentiate it with respect to the variables u and v, take the cross product of the resulting vectors, compute its length, and multiply that by the value of the function over the surface, and integrate this function as a double integral, as an integral in u and v. Okay, so let's see an example. So let's compute the surface integral of the function x squared over the unit sphere. So it's the sphere of radius 1 centered at the origin. So let's pause the video and compute this surface integral using this formula. And let me give you a hint. You should use spherical coordinates to do that. All right. I hope you pause the video and realize that we can indeed parameterize this unit sphere using spherical coordinates. Well, the angles from the spherical coordinates theta and phi. Because the points on a unit sphere can be identified, well, have coordinates, that is, for the x coordinates is the cosine of theta times the sine of phi. So the radius is set to 1 in sort of those formulas for spherical coordinates. Then you get a unit sphere with the x coordinate being cosine of theta times the sine of phi, the y coordinate being sine of theta sine of phi, and the z coordinate being the cosine of phi. And you might recall from computing the Jacobian of this transformation to from spherical coordinates to Cartesian coordinates that we have seen what these derivative vectors are, and also what their length, what the length of their cross product is. It is namely, you can check, it's the sine of phi. So you can differentiate this vector function with respect to theta and phi. Doing it component-wise, you get two vectors, of which if you take the cross product, then compute the length of that cross product, you will get the sine of theta. So that's the extra factor that will enter our integrand. But also we have to compute the value of the function along the surface. So x squared is our function now, but x, notice that this is x, it's the cosine of theta sine of phi. So what we really compute when we compute this double integral is this x component squared, so the cosine of theta squared sine of phi squared, and then we have to multiply that by this extra factor of a sine of phi. Okay, and we integrate with respect to theta and phi. Now let's just recall that theta and phi, as we go around the sphere, as we create this sphere, should change between the values. Well, theta should change between 0 and 2 pi, and phi between 0 and pi. So these are the intervals for these parameters, these variables. So theta changes between 0 and 2 pi, and phi between 0 and pi. Okay, so this is the integral we have to now evaluate. Let me continue over here with that. Okay, so, well, this integral nicely splits into a integral in theta and an integral in phi, because you can just separate, for example, you can take the cosine of theta squared and integrate that with respect to theta, as theta changes from 0 to 2 pi, and then you can multiply that by the integral with respect to phi of sine cubed. Notice that we have 3 factors of sine phi's, so the sine of phi cubed is what we have to integrate over here. Now this can be evaluated or integrated, these functions, via the usual tricks. So the cosine of theta can be written as 1/2 times 1 plus the cosine of 2 theta. The sine cubed of theta can be written as the sine of theta times the sine squared of theta. The sine squared of theta factor can be written as 1 minus the cosine squared of theta, and then expanding that gives you the sine of phi minus the sine of phi times the cosine of phi. So you that you can integrate. So let me just quickly record that. So the first integrand can be rewritten like this, while the second integrand can be rewritten as follows. And these integrals are now easy to compute. And in the end, what you will find that this integral is 4 pi over 3. Okay, so you will find the next more detailed explanation below. All right, so with this example done, now we understand how to compute these surface integrals. Let's look at a special case where the surface that we integrate over is the graph of some function of x and y. Okay, so for graphs of functions, these formulas can be rewritten in a nice way. So let's imagine that our surface is now given by the vector function where, well, x is just x, y is y, and the z component is a function of x and y, as we are used to seeing surfaces. Before, we've always thought about them as functions of some the graph of some function of 2 variables, but that's too restrictive. For example, the sphere is not the graph of just one function. So that's why this is a special case where we have the graph of a function of 2 variables giving us this surface. And if this is the case, so really our vector function is a function of x and y, and its components are x, y, and g of xy. Then, to compute this factor of the length of the cross product of the 2 partial derivatives, well, that can be computed easily. I'll leave it to you as an exercise to see that this cross product will have a length that is equal to the square root of the partial derivative of g with respect to x squared, the partial derivative of g with respect to y squared, plus 1. So we add all these up, take the square root, and that's going to be the length of this cross product. Okay, so with that, we are basically ready to reformulate this surface integral formula for the special case where S, the surface, is given to us by the graph of some function. So this surface integral is the double integral over some domain over which x and y change, and we take the function f of x, y, z, where now z is to be on that surface should be equal to g of x, y, and then we have this extra factor that we just saw of g sub x squared, g sub y squared plus 1. And this is a double integral that we have here. Okay, so that's what we are evaluating for a surface that is the graph of some function g of x, y. All right, let's see an example. So let's integrate, evaluate the surface integral of the function y over the surface that is given by the graph of the following function, well, where we have z be equal to x plus y squared, with x changing from 0 to 1 and y changing from 0 to 2. Okay, so pause the video and use this formula to compute this surface integral below. All right, so I hope you paused it and realized that this function right here is our g of xy, so it's x plus y squared. So what these terms are here, we have g differentiated with respect to x, so g sub x is now just 1. If you differentiate that function with respect to x, you get 1. G sub y is 2y. Differentiating g with respect to y gives us 2y. So those are the expressions that enter that formula. The double integral, in the double integral we have x going from 0 to 1, y changing from 0 to 2. Then we have y times that square root of 1 squared plus 2y squared plus 1. So there are two terms of 1. Then there's 2y squared, so that's 4y squared. 2y squared gives us 4y squared. So we integrate with respect to y and with respect to x. So the integral with respect to x is easy to compute. Nothing depends on x, so that's just a factor of 1 that we get there. The integral with respect to y are also not complicated to evaluate. If you think of the square root of 2 plus 4y squared as 2 plus 4y squared to the power 1/2, then you realize that this is just, well, 1/4. Well, you can take out a factor of root 2, but otherwise it's just the derivative of 1 plus 2y squared to the power 3/2. So if you differentiate that function, that factor of 3/2 cancels with that 2/3. The derivative of the inner function is 4y. That factor of 1/4 gets rid of the factor of 4, but the factor of y remains, and that's how we get this function. That factor of root 2 can be put back into under the square root, so then we have that correct, and y changes from 0 to 2. Okay, so if you evaluate this, you will get 13 times root 2/3. Okay, I hope you enjoyed this video, and I'll see you in the next one.